Okay, cool. Yeah, I'm Simeon. I'm from TDEs near Berlin, and today I'm the last obstacle between you and lunch. So let's get started. So I would talk about multi-messenger emission from TDEs, meaning photons and neutrinos, basically. To give a short overview, so first I will start with some motivation, why we do what we do, and then explain what we do. Followed by a short introduction into what tidal disruption events, that's what TDE means, are. Then I will highlight two likely TDEs that we found in coincidence with high energy neutrinos detected by IceCube. Then I will go into details on the spectacular dust echoes we found for those events, followed by a third event we also discovered, and give some kind of outlook. So why are neutrinos great? So Fotiini yesterday in her great talk already mentioned some of this. So neutrinos are great because they directly point back to sources of cosmic rays. So I don't want to step on anybody's toe here, but neutrinos are not deflected by magnetic fields. So when we can resolve their origin well enough, we can learn a lot of stuff about their sources. But detecting neutrinos is hard. And the experiment I'm part of is IceCube, which, as you probably all know, is a cubic kilometer of instrumented ice deep in the Antarctic below the South Pole. And when neutrinos interact with the ice, like traveling through the Earth, interact with the ice and then produce leptons, which then produce light, which we can detect. And on the right side, you can see the typical event view of one of those high energy neutrinos arriving. And what you can see color coded here is basically timing information. And from this timing information and from the spatial distribution of the different photomultiplier tubes that are in the ice, we can infer the direction the neutrinos come from, usually on a level of a few square degrees to a few tens of square degrees. Yes, but not only is detecting neutrinos hard, identifying their sources is also a challenge. And as probably all of you know, in 2013, IceCube detected the first hints of a cosmic high energy neutrino flux, which you can see, which I quite prominently highlighted here in red. That's this excess region in the higher energy part of the neutrino spectrum. And so far, there has been one very compelling source, a gamma ray flaring blazar TXS 0506 plus 056, which was discovered in coincidence with one of those high energy neutrinos in 2017. Yeah, but at least 70% of the flux remains of being of unknown origin. And Fotiini yesterday had this great overview where we're able to see that, like, for each source class, there are quite stringent limits on how much of the total flux of neutrinos can be explained with those sources. So it could very well be that we end up with like a lot of different sources contributing each like in the low percentage digits. But it could also be that like we have a dominant source class, which is basically hard to identify right now because it's very redshifted. So at the moment, we don't know. But to highlight some of those source classes, so there are GRBs, various types of supernova where there's some kind of interaction with the surrounding material, for example, in the type 2N, where you have a circumstellar medium, which can produce high energy neutrinos. Then there, of course, are tidal disruption events, and active galactic nuclei are also thought to be able to produce neutrinos. So our follow-up program, which I will go into in a few seconds, is basically able to detect those sources highlighted here. GRBs, we're not sensitive to GRBs basically just because they evolve quite fast. So we miss out on those. But of all those sources we can possibly identify in the optical, I will today only talk about those two. Mainly about tidal disruption events, but also a little bit about AGN, because we think there is maybe some slight overlap between those two sources in points of neutrino production. So what do we actually do at DESY? Well, there is IceCube sitting at the South Pole, And whenever IceCube detects a high energy neutrino that meets certain criteria, mainly being that the probability of it being of astrophysical origin is high enough, so above 30%, an alert gets disseminated globally, and we receive this via email or, like in our case, via Slack. And then we get to work, and then we have, like, a part of my PhD was basically making myself and my colleagues redundant in that process. So we calculate if this neutrino meets our own quality criteria, which is basically the localization and or the probability of being of astrophysical origin. And then when we observe this neutrino. And we have arrived at a point where just can, like, press a button, and then it's like the telescope is triggered automatically. And this telescope is ZTF, which is short for the Zwicky Transient Facility, which is a great telescope that's located on Mount Palomar in California. So it's a Schmidt-type telescope, was built in '48, I think, and it has recently been re-equipped with a state-of-the-art 47 square degree CCD camera. And this field of view, which you can also see here, like in comparison to, like, for example, its predecessor or Pan-STARRS, and also LSST, which will come online next year, I think, or maybe even this year. So it has a huge field of view, which makes it great for those kinds of follow-up, because, like, when we are usually able to cover the whole uncertainty region of the neutrino with 1 or 2 telescope pointings, which basically saves telescope time and allows us to be systematic in covering the whole region. Now, when we do that, we get an observation, hopefully, and then a lot of alerts. So ZTF is one of those, like, since 10 years, new type of sky survey telescopes that basically scan the whole sky every night. So we get new data points for objects with a cadence, meaning a frequency of two days. So a new data point every 2 days. But this produces tons of alerts. So ZTF has around 300,000 alerts, meaning new stuff is happening per night. So we need to do some filtering, and we use AMPL, which is software developed at Humboldt University at DESY, to filter all those alerts, meaning they must have stemmed from the 90% sky localization of the IceCube neutrino, and they need to match several other criteria, meaning have a high probability of not being bogus, so being real alerts, and so on. And when we've done this, we trigger additional observations for those candidates that are interesting and pass our quality criteria. So we do spectroscopy or radio observations and so on. Yeah, and we're at the moment working on making this also automatic. So, and as you can see, we have followed up roughly 1/3 of all IceCube alerts. Some of them we chose not to follow up because they were too poorly localized. Some of them we could not follow up because it was day in California, but roughly 1/3 we can follow up. And now let's get to the next part, is what are tidal disruption events? So, as many of you probably know, it has been theorized in the 70s that maybe what happens if a star approaches the supermassive black hole in the center of a galaxy too close for its own good. Well, it then gets ripped apart by tidal forces, meaning the front of the star that's closer to the black hole has a gravitational pull that's much larger than the back of the star. It gets stretched apart and then gets accreted around the star. So we think that roughly half of the mass of the star is quickly accreted into an accretion disk around the supermassive black hole. And these events can be bright for months in the optical or in the X-ray. So what you can see here is the SED of a host galaxy pre-TDE, and when the TDE happens, you either get optical emission, which can be approximated by a black body in the 10⁴ Kelvin region, or an X-ray black body. And it's at this moment not clear if these are two distinct populations or if we just have, like, geometric effects from viewing, like when the accretion forms, there could be jets, and it could be that when we look into the jets, we see the X-ray emission, and when we look side on, we only get the optical emission. But that's like one of the open points right now. And the great thing is we are getting better at detecting TDEs. So ZTF, but also Pan-STARRS, Gaia, Atlas have been very helpful in finding these, and not Atlas, Assassin. So the numbers have risen dramatically in the last years, but still we only have around 100 objects. So that's not a large population we're talking about. So a lot of stuff is not known about TDEs yet. But the first object I want to present is 82,019 DSG, or because like our internal abbreviations, the ZTF internal abbreviations are even worse than those TNS ones. So it was known as ZTF 19AAPEREIS, and because it's very unhandy, we decided to give them names of Game of Thrones characters. So sadly, even after season 7 and 8 of Game of Thrones happened, we still have to stick with this naming scheme. So that's what we do. So this is Bran Stark, and you can see the light curve of the event here, and what you can notice that it's quite long-lived. So this is days here on the x-axis, and in red and green is optical emission as measured by ZTF, and you can also see that it's bright in the UV. And the most prominent thing to notice here is that this dotted line denotes the arrival of the high-energy neutrino. So this event was already 5 months old when we detected it. And then on a more sinister level, a year later, like half a year after I started my PhD, we found another event within the sky localization of a high-energy neutrino. So this was a neutrino detected in May 2020, and it was dubbed Tywin, like after this sinister guy here. And this is a bit peculiar. I mean, this is the main object we wrote this paper on. So this is not a clear-cut tidal disruption event. We think it is one, but it's a little bit more complicated because its host is a narrow-line Seyfert 1 galaxy, meaning it's an AGN. And in the beginning, and even like a long time after that, a superluminous supernova type 2 origin for this event was debated, but we think it's a TDE, and I will get later into that. And it's quite far, and that's the mass of the black hole in the center of the galaxy. So this is how this event looks. So now just look at the bottom part. Here we have like the G band, meaning the green optical emission as measured by ZTF, and two things to notice that this is even more long-lived. So we have around 800 days here, and we can still detect this event. And also here, the neutrino arrival was way after the optical peak, which is peculiar and got our theorists thinking and working. And on the top part, you can see 3 SEDs from 3 different epochs denoted in gray here. And as you can see, we were able to quite well approximate this with 2 black bodies. One black body capturing the optical and the UV emission, which declines over time, and a second black body in infrared that, rises over time. This is also something I will get into in a second. And what is remarkable about this event is that it's one of the most luminous transients we ever discovered. So it has a huge bolometric energy. We did radio observations for those two events. For Bran, it was great because the radio showed clear signs of evolution, hinting at some central engine feeding the event. With Tywin, it was, sadly, we first thought we see signs of evolution over the course of 5 months or so, but then we decided that, it's probably a calibration artifact. So what we're seeing here is probably, there is a detection in the radio, but it's probably from the pre-existing AGN and not the TDE itself. Tywin was also observed by eROSITA, which is a German, or SRG eROSITA, which is a joint German-Russian mission that's on hold, sadly, right now, but it was still operating during that time, and this also scans the whole year with a whole sky with a half-a-year cadence. And we detected this event, like this Tywin event, on the 3rd visit. So on the 1st and the 2nd were a non-detection, but the 3rd detected a signal, and what we got was a very soft X-ray spectrum with a black body temperature of around 70 electron volts, which we interpret as evidence of it being a TDE, because it is very unusual for an AGN, even if it's a narrow-line Seyfert 1 galaxy, to have such a soft X-ray spectrum. And it is also quite unusual for a superluminous supernova to have an X-ray signature at all. Yeah, and TDEs have been suggested as sources of high-energy neutrinos in the literature in the recent years. You can see a small selection here on the right side. And what is basically argued for is that when you have this accretion around the black hole, there, like in our case, we for our paper, we looked into 3 different origin regions for this high-energy neutrino. So either a jet, which, grain of salt, we have to say we have no clear evidence of having observed a jet, the accretion disk itself, or the corona of the accretion disk, and some mildly relativistic outflow. This could, yeah, and both, like all 3 scenarios are indeed compatible with like the observed neutrino. So, but I mean, we do not get a neutrino expectation of 1. It's like at most 0.05 or so, if I recall correctly. But I mean, if you take into account that there could be more of those sources, and we check on average, then just get 1 of 20 of those sources, this basically fits the picture. So we concluded that the neutrino could have come from that source. So that's a quick picture of the luminosity of those 2 sources. Tywin has a much higher luminosity, but when you take the redshift into account, they have comparable flux on Earth. And if we take the flux, like the optical flux, as a proxy for neutrino flux, both have around the same probability of yielding a neutrino that we could detect here. So that's like a small comparison of both events. So Brian was a TDE, Tywin was likely a TDE. Both were detected in radio, both were bright in the UV, both had soft spectra, and both had a dust echo. And in both cases, the neutrino was delayed with respect to the optical peak. So we took this as a combined population of confirmed TDEs and so-called accretion flares, where we have events that look like Tywin, which are not a clear-cut TDE, but like in AGN have these long-lived flares. And we threw all those events together, applied some basic cuts in brightness, rise time, fade time, and so on, and then used this to combine to calculate a combined chance coincidence. And we ended with a 3.4 sigma probability of finding 2 such events in the ZTF high-energy alert neutrino footprint that was like accessible to us in our follow-up program. Yeah, and let me, because we have this like nice picture from our DAISY PR office, let me quickly get into this dust echo thing. So ignore everything then the light curve here on top. What you can see here is not only the G band detected, but also, like I already mentioned this with the infrared black body, and we also got WISE W1 band detections, which begin to rise after the optical peak. And we interpreted this as some kind of dust echo, which you can imagine works like the following. So we have the supermassive black hole that is surrounded by a dusty region. And when this TDE happens, here something explodes in visible light. And the dust immediately surrounding this region gets burned away until it's so far out that it just merely starts to glow. And when this dust is starting to glow, you get dust from the line of sight to the tidal disruption event. You get this immediately. But then with a time delay, you get dust from this inner shell that is perpendicular to the line of sight. And then at the end, you reach a peak when even the light from behind the tidal disruption event within the dusty shell reaches us on Earth. So and this all fitted quite nicely. And from that, it's also cool because you can then infer some basic geometric information about this dusty sphere, and we inferred a radius of this dust sphere of roughly 0.16 parsec. And then when you take the optical luminosity and the dust luminosity, divide them by each other, you can infer how much of the sphere is covered by dust that can then re-emit the light in the infrared. Yes. So, and now we asked ourselves to bring this journey to an end. Bran had a record-breaking dust echo. So in terms of how much higher the flare was compared to the baseline prior to the optical flare. Also, Tywin had a very strong dust echo. Is there more? Could there be more events that share those properties, meaning they had an optical flare plus a dust flare? And there is, surprise. So this brings me to a last event, which is dubbed Lancel, which is this young guy here. And a collaborator of us, Sjord van Velzen, did a systematic study where basically took all the IceCube public high energy alerts and all the optical flares in ZTF that showed a post-peak flare detection by NeoWise, and when you combine those, you discover a third event that lies within the uncertainty region of one neutrino. This was one of the alerts we did not follow up because it was daytime in California, which you can also see here. So it was not covered by ZTF during the time when the neutrino happened because it was just, it was day. But when we did this like in an archival way, we uncovered this event. And also here, we have a delay of the neutrino signal compared to the optical signal. So in all those three have a strong dust echo, have a soft X-ray spectrum, and all were detected in radio, which then brought us to the point, and that's just like a flux comparison, brought us to the point that, and when you do a chance coincidence for combining those three, you end up with 3.7 sigma. So it's not like a linear growth in sigma because when you include more events, of course, like also the sky region that you scanned with your telescope increases. So this might hint that TDEs and what we dubbed as accretion flares might be some kind of unified population, because also when you have extreme flares in AGN, they must be triggered by something. So Sjord argues in this paper that maybe they're just two ends of like a spectrum, right? So you have a clear-cut TDE in a quiescent galaxy on the one hand, and something that could be an AGN flare triggered by a TDE in like more active galaxies, which is also something that this is interesting here. That so further thought, we have like those events where we have a strong dust echo, and these allow. So TDEs can happen in those, right? Because the supermassive black hole is not so massive that the whole event basically falls into the supermassive black hole. So if this nice corner where all these three events detected live, it could be that there are more. So to conclude, we have found three high energy neutrinos coincident with these accretion events plus TDEs, and these can produce more than 7% of the IceCube high energy neutrino flux, right? When you just add those events up and use their probability of being of astrophysical origin, right? Remember, not for all of them, we're just like 60% sure that they're cosmogenic anyway, or cosmic anyway. So you end up with this number. But normal AGN outshine TDEs by like 2 orders of magnitude because they're much more numerous and inject much more energy into the universe. So, and we're not dominated. We don't see a clear signal of neutrinos from AGN. So if these associations with the TDEs and the TDE likes are true, this hints that there must be some very efficient neutrino production in TDEs. We'll see. So, and there's a systematic second analysis of dust echoes with all the neutrinos, like not only the high energy neutrinos, but all the neutrinos going on. This is done by Jannis Necker at DESY. He will give a talk about this at TEFPA, so I don't want to take the butter from his bread. So you have to listen to his talk when you want to know what comes out of this. And the universe will tell us more, right? So we, of course, will continue our real-time follow-up program. ZTF will operate at least 1 more year. We're at the moment doing a systematic study of all the nuclear events in ZTF and all the infrared flares detected by WISE, and it's going to be very exciting what comes out of this. And of course, there's LSST coming, which will allow us to look much more deep, which will be challenging in its own way. So to give a brief summary, we have doing this follow-up campaign for 3 years. We've detected 3 events coincident with high-energy neutrinos. We're conducting a systematic analysis of dust echoes due to accretion flares at the moment. And when you do this with the high-energy neutrinos alone, you end up at a significance of 3.7 sigma. That's it.